So I will discuss today about one of my favorite equations, and I'll explain that in a second of why it is. But so there's like a little picture of Florida International University. Probably you don't see any alligators, but we do have those as well here. And it would not be really
I wanted to make that joke actually. I was thinking about that joke.
Right. Well, you're right. I have to. So it wouldn't be work done if it wouldn't be for my collaborators. And this is done together with several people. And I will show some theoretical and some numerical results. So with Luis Farah from Federal University of Minas Gerais in Brazil, with Justin Holmer from Brown University, with Kai Yan, he's a postdoc at Florida International, with Christian Klein and Nicola Stoilov in Dijon, France, although I think Nicola just moved to Paris recently. Okay, so, well, let's start with the equation. So let me see if this works. Yeah, I think you can see my pointer. So the equation is derivative in time, and then in x we have in n dimensions, we do have a preference in first dimension x1, and we take p different nonlinearities. So what do we recognize if x is one-dimensional? It's the kdV, or generalized form of it, right? So we have three derivatives on u, and if p is equal to 2, this is just regular kdV, 3 modified kdV, and so on. But if we take r x and r3, okay, then we see that this is the equation. So think about this Laplacian as uxx, uyy, uzz, and then we have a derivative in x, x1, that's the preferred direction. So that's the equation which was introduced by Zakharov and Kuznetsov back in 1972. And I like to show this. So this was back in Soviet Union in 1972. It says three-dimensional solitons by Zakharov and Kuznetsov. And there's a formula for the equation, and they derived even some conservation laws, which I'll talk about. So it's kind of interesting to talk about the equation. Why is it favorite? Because as some of you, I can see like George, for example, here, and probably Simon might remember that back in 2017, we had the meeting in theorem, and this is Zakharov and this is Kuznetsov, had often heated debates, well, about solitons or physics. And just a year before the pandemic, they're still debating. So it's kind of nice to talk about the equation where they're still discussing and have heated debates. So in any case, but of course, they formally just introduced the rigorous derivation was done later by Lance Linares and Sod, 2013. And there are different other applications, so derivations in the 2D, in the 3D, and so on. Okay, so as I said, there are conserved quantities. The main one is the mass, the L2 norm. There's a Hamiltonian, or the energy, the standard one, as in dispersive equations, you have the gradient, or they have a kinetic energy minus the potential. And then there is the L1 type, L1 type, where you just integrate in the x1 derivative, x1 direction, or in kdV, it would be just integrating in the space direction. And I call it L1 type because it's purely just the integration of the equation. So if this would be kdV in 1D, of course, this would be integrable systems, and we would have many more, well, infinitely more conserved quantities. However, zk is not integrable. And we will see this, for example, in interaction of the solitons, or just how the solitons travel. In particular, well, I'll show you in 2 and 3D pictures. Okay, so one of the important things is the scaling, or scaling invariance. And basically the time has to be dilated with lambda cubed, the space with lambda, and then the normalization in front, it's the p over power 2 over p minus 1. So what this does, it makes the Sobolev norm basically scale invariant. So if this is equal to 0, then we get exactly the scale invariant index. And the main cases which we typically want to consider is s equals to 0, or s less than 0, and s greater than 0, right? So the first case will be called L2 critical. And if you think about n equals 1, then that's exactly p equals 5. This is the case of gkdV, the quintic power. So in 2 dimensions, p equals 3 for the zk. Sometimes it's called modified zk equation, which is important. And the one which we will consider in dimension n equals 3, which is p equals 2, that's the zk. This will actually be the subcritical, and it will determine, so I have sort of like an empty slide here, behavior. So we are interested in the global behavior of the solutions. And what are the typical solutions in the dispersive or wave type equations? So we think about some kind of the wave or coherent structures traveling, right? And so what it means is that with time, it probably preserves the forms. There is maybe some radiation. So this is kind of a schematic radiation. But we do want to understand what the solutions are, how they behave globally, and how they form, for example, the solitons, and whether they're stable or not. So before we can talk about the solutions, of course, we need to understand what the solutions are. And one of the things here is the well-posedness, which includes, so we have existence, we have uniqueness, and we have some kind of dependence, like usually continuous dependence on the data. So if we start with p equals 2, so we in zk equation, which has, so remember we had, so we do it like this, dx1 of u to the p, that's the nonlinearity, and p equals 2, that would be the standard, like in the kdV or standard zk equation square. So what do we know about this case? So this is s less than 0, it's a subcritical, so we expect that probably the solutions should exist globally. In fact, I didn't really mention that we can also consider the focusing, defocusing cases, but I typically consider just the focusing case. And investigation of solutions started by Fominsky in 95, where he considered the S integers and obtained the local well-posedness and global well-posedness for integers s greater or equal to 1. Linares Pastor got a local well-posedness within HS with S greater than 3/4, so they lowered down to the 3/4. And as in all a typical game for the well-posedness is basically how far down can you go with the index S, determining for the local well-posedness. So there were 2 works by Green, Rock, and Hare in 2013 and Molyneux and Pelot in 2015, where they brought the S down from 3/4 to 1/2. And then quite recently, Kinoshita in 2019 showed that the local well-posedness can actually go all the way down to -1/4. And so we expect the global well-posedness to be in S greater or equal to 0. So for example, L2, where the mass is conserved, is the essential part. So we can consider, so for this p equals 2, and this is the 2 dimensions, we can consider, for example, L2 data. Although for our purposes, we really need the finite energy data, which is in H1. Now let's look at the p equals 3. So this is where we have cubic nonlinearity, like in KdV, that would be the M modified KdV, or sometimes it's also for 2 dimensions called modified Zakharov-Kuznetsov equation. So it is a critical case. So critical case means that there is a delicate behavior between between the focusing Laplacian and the power, and defocusing Laplacian and the focusing power. So here we have the game started with Linares Pastor in 2009, obtaining the local well-posedness in S greater than 3/4, and global well-posedness a little bit less than 1. So then Ribot and Vente improved it to 1/4. And then we had the work for a global well-posedness using the I method for to basically bring this down to 3/4. And local well-posedness recently was obtained by Kinoshita as greater or equal than 1/4. Okay. And so this is for the L2 critical case. So let's look at now for other P's, because this is also an interesting and quite unopened territory to look at various things. So this is the so-called L2 supercritical, where S greater than 0. So typically we expect in the supercritical case, and especially in the focusing, we expect some kind of instabilities and formation of singularities like blow-ups. But for the local well-posedness, right, so for the local in time, the result is by Linares and Pasteur for P. So P is the power, remember, so the P is the power, we take dx1 u to the P. And this is the P in my notation. In literature, sometimes it's not the P, it's K plus 1, for those who are familiar. So the local well-posedness for P less or equal to 8 was done for the S greater than 3/4. And then the improvement was for S, which is greater than S sub C, for P greater or equal to 8. And then in P greater than 3, you can also get the global well-posedness, so-called math energy threshold, which we introduced with Justin Holmer back for the NLS equation. So this is depending on the gradient and on the mass on with the dichotomy. But for the local well-posedness Ribot invented, that's probably the best result. For P equals 4, the local well-posedness was S greater than 5/2, and starting from 5, that's the optimal result, S greater than S sub C. So this is for the 2D. I'll mention the 3D. So 3D, this means that S sub C is less than 0, so it's subcritical. So we expect in this equation solutions exist globally. So what do we have here? Linares and Sot in 2009 got local well-posedness for S greater than 9/8. So notice that this is greater than 1. And then it lowered down to 1, but not including 1. Reborn Vento, we got the local well-posedness here. They actually got almost H1, but well, B11. So there was just the logarithmic summation, which is which was missing to get down to the H1. Then Molyneux and Pilot obtained global well-posedness for S greater than 1 in 2015, and it stayed for a while. And this is what we've actually used as well in our considerations until very recently. Kinoshita showed that, well, actually you can go all the way down to the S greater than -1/2, nearly optimal, meaning that optimal would be, optimal would be if they would be equality sign here. And so, for example, global well-posedness can be considered not only in the energy space, and we would want to have an H1, but actually you can go all the way down to the L2 space. So this is what's known for the 3D P equals 2. Of course, there are several open questions here, which I'm not going to talk, but I'll just mention. So for example, what happens when P is greater than 2? Do we have any kind of well-posedness? What happens in other dimensions? For example, when the dimension greater than 3, right? So there's some work on the well-posedness recently by also by Sebastian Hare and Shinya Kinoshita for the dimension greater than 3. In terms of the local well-posedness, but other questions are not really investigated there, but that would be interesting to see. Okay, so now we talk about the coherent structures. So that's exactly what's interesting in this equation, and how this equation was even introduced is to consider the solitons and their stability. So one of the very nice features of this equation, it sort of lets you study higher dimensions while really having kind of one-dimensional preference, meaning that our our traveling waves or solitons will be really traveling in just one direction, which is there's the x1 direction and only in the positive direction. So that's why I wrote c squared, just to indicate that it's positive speed. So what is the q sub c? It's the dilation appropriate to the p, and q is the solution, which is the ground state solution of the famous, well-known, this nonlinear elliptic equation, which shows up not only in kdV, but in MLS, in Klein-Gordon, and we're typically very familiar with that. Just to mention, is that in 1D, so, and that's what's the beauty about this equation, that in 1D, the Q is solved explicitly, right? So, and because you have the formula, then whenever it comes to the linearized operator or any kind of studies, it's explicit, it's nice, and so you can understand or derive lots of things with it. However, in high dimensions, there is no explicit formula. Nevertheless, for dimension greater or equal than 2, the Q decays exponentially, so it's still the exponential decay. It's still radial, it's still positive, decaying at infinity. And let me mention back in the 1D, the following formula for the L2 norm of the Q sub C. So we notice that if we just calculate the L2 norm, then 5 minus P shows up on the top, and that's exactly says that when P equals to 5, then basically that equation, right, does not feel the size of these dilations, right? So that's why we expect that something bad can happen, so right, so it can lead to the blow up. And indeed that's the case, which I'll mention next, or it comes after a few slides. So the main thing about the solitons, and this audience seems to know quite a lot about the solitons and stability. So, but I'll review it anyway. Is the stability or instability of solitons and characterizations like that. So. First of all, let's look at the notation. We have a so-called tube. So what's this U sub alpha? That's a neighborhood of the soliton Q sub C. So C is dilation, remember? And there's a X, we incorporate also all the shifts in the Q. And so if we stay close, so here's an H1 norm. If we stay close, then we call that we're staying in this tube U sub alpha. So the orbital stability is basically says that you start in the tube and you stay in the tube, possibly maybe with a different, if it's not alpha, maybe it's a slightly different size of it, but you stay there. However, and it's great, it's good to know, because that's one of the things it's important to understand. If it doesn't hold, then it's unstable. But a little bit more interesting is the asymptotic stability. Why? Because a priori orbital stability just says that, well, we have some kind of approach of the soliton, but the actual solution can wander around the soliton orbit, right? Because it's not really specific what happens at the end. So asymptotic stability is a little bit more delicate, meaning that we can exactly specify how the position and how the speed of the scaling parameter behaves, okay, as time goes to infinity. Again, I'm talking only about the H1. Of course, you can always ask questions about different spaces, but so. And to talk about the stability, I'll go back to KdV equation, or generalized KdV equation, where the orbital stability was obtained for P less than 5. Remember, this is the L2 subcritical case. That's where that criticality index S comes into place for P less than 5, and unstable for P greater than 5. That goes back to the original question and work of Benjamin in 72, but then really it was Bonus, Uganigis, Strauss, and extension of Gerlachis, Chatain, Strauss, 87, and Weinstein in 85. So the asymptotic stability was investigated first by Pego and Weinstein in 94, where they look at the exponential weights, and then there are several works. I'm just mentioning just a couple, but there's plenty of works on this subject. And I'm sorry if I'm not mentioning all the people who worked on this question. So the delicate case, as you can see, is p equals 5, right? And is the soliton stable or unstable? Turns out that it is unstable, but this was a quest, quite a quest to actually get that, because like unlike in the last, you can have virial, or you can show that there's a blow up and that instability would imply. But here we don't have a suitable virial, which could help us with that. So instead, what happens is that Martel and Merle, they investigated back in 2000 and introduced certain characterization of solutions near the soliton Q. So one of them was is the Liouville theorem, and this is the one which is really tells you things like rigid things for sure. Like if we remember a complex analysis, right? The bounded functions, bounded entire functions turned out to be nothing else but the constants, right? So this is a sort of type like where you know that something is bounded in a certain norm, that it can be nothing else but a soliton. So then they were able to show the instability of the solitons, and together with instability, a non-linear version of the Liouville, which sort of replaces some kind of a, replaces or gives something instead of the virial in NLS. Merle was able to show the collapse, so prove the collapse, finite and infinite time. To show that it's a finite time, this is where there's a little bit more delicacy comes in, is that you need to control the tail, right? So you need to know how the solution behaves and exactly like how it decays. And depending on how it decays, so for example, in this case is that if it decays in like a little bit better than, I guess, x to the 5th, so whatever the power is, then that's sufficient to guarantee the finite time of the blow up. And so the blow up was not known for a while, right? But it goes back to numerical works of Bona and collaborators, as well as Dix and McKinney. But that's back in last century, where, although it's amazing that they were able to do some of the calculations, because unlike NLS, this is where the soliton is moving and it's blowing up on the top. One of the recent papers was by Christian Klein and his postdoc, where they exactly confirmed and discussed and showed some of the blow-up situations. So p equals 5, that's the L2 critical. And let me show you the picture because it will be easier to understand. So if we start with the data, which is slightly above the Q, this is the U soliton Q. So here's the starting moment, t equals 0. Then what happens with time, that it's starting to grow, right? But you notice that there's a little bit of a radiation showing up, right? So that's exactly where you see that it's a non-integrable system. Okay. It progresses. You can see that they're like at time 21.5, it keeps growing. There's a little bit of radiation going to the left, but it keeps growing, and it will, and it's also, as it grows, it goes faster. So eventually it blows up. What does this mean eventually? Of course, numerically, you can't, you just see this grows, and then you say that it blows up. But as I said, Martel and Merle showed that you can have the finite time blow up in this equation. Now, for the 2D, this is where we start coming to the ZK equation. What you can see is that, so this is for the modified, so the power is cubic. So the solitons, you can see that they are traveling. So for example, we started at 0, so it's traveling in this x direction. I'll show better pictures, but this is just to start getting a little bit of a taste of what's happening. You can see there's a little bit of a radiation coming over here. So this is what's happening, and that's the computation with Christian Klein and Nicola Stoydov. So what do we have in this modified ZK equation? So this is the L2 critical case. Well, we were able to show that we do have a blow up or collapse in following the ideas of how it was done in Martel and Merle. So we showed the infinite or infinite time, but again, posing the decay condition on the initial condition, it should be possible to show a finite time. That would be a nice problem to look at. And again, the theory, since it's basically a lot of perturbation, we only show for the mass, which is slightly above the mass of the soliton. However, numerically, we can take all kinds of initial data, and what we see is that indeed there is a profile Q which shows up the soliton profile, right? So it's traveling. So how do we know it's traveling the next direction? So you can see that X is changing, and capital T is the blow up time. So the blow up time is the finite time. And y prime is just one specific coordinate which it will approach or basically stay. But you notice that the next star, what happens with little t going to capital T, right? This goes to 0, so the x star travels to infinity, and that's typically what we observe in L2 critical blow up. So the blow up happens at infinity. This situation changes if you go to the L2 supercritical, so the blow up happens at the finite location. But okay, so what else do we see? We see that L of t is square root of t minus t. So the behavior or the blow up rate, how it happens in the ZK as a square root of t minus t. So I should have mentioned that the description of the blow up in gkdV, similar to this, again, close to the mass of the soliton, was done in a series of papers, I guess around 2014-15 by Raphael, Martel, and Merle. Okay, so let's look at the stability of the traveling waves. Obviously, we can see that in the case where we have a blow up, probably that generates the instability, but in general for different P, okay, so I'll recall that P critical here is 1 plus 4 over n, right? So in dimension 2, we have P critical to be 3, okay? And in dimension, equals to 3, P critical will be something like 7/3, which is greater than 2. So the situation is very similar. The solitons are orbitally stable when they are in the L2 subcritical case, and unstable when P is greater than the critical X power exponent. And this was shown in 96 by Anne de Boer. What she did, she revisited the gkdV methods of Bonas-Uganiki-Strauss and Grelakis-Shatas-Strauss. So of course the question is what happens with P critical, although since we now have the blow up, so P equals critical condition, at least in 2D, the solitons are unstable. What can we say about asymptotic stability? Okay, so back in 2014, there was a very nice paper by Kot, Muniz, Pilot, and Simpson. What they did, they tried to adapt the Martel-Merle work on asymptotic stability for generalized KdV. And they were able to actually extend not only for P equals 2, but a little bit larger. So there's a specific, but one can notice that it's definitely less than P equals 3. So there was a question, can this asymptotic stability hold up to P equals 3, and then exactly what was happening at 3. There are some other, they also did the stability of decoupled solitons, and there's a recent work by Frederick Vallée, I think, in 2020, existence and uniqueness of multi-soliton. So he did for P equals 2 and 3, in 3, of course, under the condition of the ground state. And I think he also did the 3D regular Zakharov-Kuznetsov equation. So soliton stability, so let me see what I wanted to show here. I guess what I wanted to show is that if we start with initial data, for example, which is something like not necessarily soliton, we can see that it travels, and we start seeing that radiation. And so this is the first mention of this angle, 60 degrees. So I will be talking about this angle a little bit more, but we can see that it's basically 30 and 30. Well, I mean, there is an angle of the radiation happening, but we will prove that it's exactly the 60 degrees. This was actually for the 2D regular ZK was shown in the paper by Munoz and collaborators. We also showed this in the 3D, as I'll mention. So I'm just checking how the time is going. So I think I will probably, yeah, so let me just, this is the part, like if you would be in a real presentation, then this is where you can kind of wake everybody up and show some movies so we get back on track and ready to listen to the second part of the talk. So I want to show you a couple of movies, how things happen in a 2D. And again, this is with Christian Klein and Nicholas Stoilov. So let me see if I can get this going. Takes just a little bit of a moment to upload. Okay, so what's happening here, of course, I'll replay this one more time. So first of all, notice that this data is not a anything like a single bump. So it's kind of a sometimes called as a wall. And what happens was that it starts. So it's split on the edges into basically kind of like two solitons first. Nevertheless, because they're so close, they join. And since it's enough mass, it continues to blow up. And what you can see is that there is also radiation, little bumps on the left coming out, right? And it continue going to the left, but the blow up continues going to, actually, no, it's not the blow up, it's just the traveling of the soliton. So we got this soliton here, and it just continues traveling. Okay? So that's one of the pictures. Let me show you how the interaction of, is this the interaction? Let me just remember what we have. I think this is where the two solitons, right, so they're very close to each other, so they join and then they start traveling and the radiation is forming. So let me just, I can replay this one more time. So this is when right, so because if the solitons are separated apart, and as it was shown in some of the theoretical works, they will just travel and keep the shape. But when they're quite close to each other, so here we really take them quite close, then they basically see each other, form a joint soliton, and then spit out the radiation. Okay, something else I wanted to show here. Yeah, so I guess this is nice. So what we start here is, it's actually the Gaussian, but sorry, just start this all over. So it's a Gaussian, but it's a little bit like a squished. And what happens was that, so it starts getting into the shape of the soliton. You can see that it's starting to spit a little bit of the radiation in this specific way. And then it gets to the height what it wants to be, and then it goes to and then starts traveling. But the interesting part here is, excuse me, so if you notice, then there are a couple more bumps after that, and they also travel to the right, which means that there are solitons forming in that. So this is sort of like why I call it toward the soliton resolution, because you do see that the data, which is separating into the main soliton, and then it keeps forming the solitons, which travel a little bit slower, but and even after that, you can see a couple more at the end, which also travel, but the rest is the radiation, which is going to the left. Okay, so let's come back to now to the 3D. Okay, so in the 3D, I'm considering the quadratic nonlinearity, so just the standard Zakharov-Kuznetsov equation. And going back to the question of the stability, in particular the asymptotic stability, but also it's interesting to investigate the soliton interaction, the radiation, and eventually the soliton resolution conjecture. So at the time when we were looking at this problem, we had no H1 local wall posedness. So we developed the methods which can be incorporated where you don't have enough of the well posedness, and so you can boost the regularity as needed. So what we wanted to show is, so Andy showed the orbital stability of the solitons. So we wanted to take this orbital stability and show that the solitons are asymptotically stable. So we introduce just a parameter basically of the orbital stability, or alpha orbital is stable. So it's just the parameter alpha where we can, so we take the Q, this is our soliton, but we rescale the, so it's in the framework of the soliton. We can think of like we're moving with the soliton, and our solution has the location and has the speed or rescaling parameter C, and so we stay within this parameter alpha. If we look at the mass conservation, what it does, that it basically tells you that C of t should be staying very close to 1. So that's just the speed that we're taking was part 1. So we're staying very close to the alpha. And then in terms of what Dubois really proved, taking into the consideration the well-posedness in the class of Ribot, Vento, and Molyneux-Pilote. Remember that this was in the HS for S greater than 1. Okay, so if we start, basically what you showed, that if we start with the initial data, which is close to the soliton within alpha in H1 class, right? So this is just initially how we start. Then she shows that U is alpha orbitally stable. So it stays in the same class. Okay, so let's say we start very close at time t. So let's denote by epsilon. This is exactly the difference between the soliton and the solution U. Okay, so we have these two parameters. And we can choose this parameter such that our solution, or the leftover epsilon, would be orthogonal to certain directions. So these are the directions which come from the linearized operator. And the first 3, that's just the gradient, basically. These are pretty standard. And the third one, this is where it differs, for example, from the work which was known for the 2D. So we look at the equation for epsilon. Basically what we do, we linearize. So the linearized operator over here on the x, and there's a bunch of different parameters coming up, and there's the epsilon squared, okay? So using the orthogonality condition, it gives us some control on the parameters. In particular, for example, you can notice that we get that this parameter will be controlled by the alpha. So what does this really say? So A prime, right? So A is the location, A prime is the speed. So basically this says that we basically only traveling in the x direction, kind of like this, with the speed 1 over c squared. Okay, so now we're ready to see the statement of the theorem. And the theorem says that, okay, so for normalization purposes, so we can take m of u equals to m of q, but of course we can renormalize if needed. So we take the solution of the 3D zk, and we say that they are asymptotically stable, meaning, so the parameter is c of t, right, is this one. It converges to c star, which is really close to 1. Then the A prime, so that's the location or the speed will be 1 over c, and in direction of x, it converges weakly in h1, which will be upgraded then to the L2 convergence, this L2 convergence, and then this funky thing here, but it turns out to be nothing else but that cone was the angle pi over 3. So to understand that, here's the picture. So we're staying in the neighborhood of the soliton. So this is where the soliton, so think like this is where the soliton location in its framework of the soliton. So then everywhere outside over here, this is where we have asymptotic stability. Okay, so this is where this will come. We actually can show that there's also decay over here. There's a little bit, but numerically that's actually quite difficult to see. And then there is this region, which is over here. Okay, this is where exactly the radiation happens. And that angle is, so if you look at, here's the angle, 60 degrees. So it should be 60 degrees. So then over here, you can see that that would be 30 and 30. And that's exactly what we're seeing in the, so the theorem says that's the angle that we see. That's that cone. If we can also rescale when the soliton is moving, so but the cone will have the same size and the angle. Couple of things. So let's see how I'm doing on time. So the class, right. So what are the new features in this result? First of all, we consider the so-called class B solutions. So these are solutions which are not in H1. Then the approach which I guess Martel and Merle introduced back in gkdV is that to consider a weak limit, to sort of take all this radiation, and this weak limit will be the will help to get this solution, which will turn out to be exactly the soliton, and that's why the asymptotic stability will follow. However, we introduced the regularity boost because remember we don't have H1, so we found the way to use that via the virial and upgrade that. We look at the conic monotonicity. So also there are some upgrades in the high regularity of the epsilon, so we can use just the sort of like really virial without the regularization, for example, the regularization which is needed if one considers something like Benjamin-Only equation. And then the new virial and Liouville theorem, this is really the key properties, and it would not be possible to get anything if we wouldn't understand the spectral property, but because of the soliton is not explicit, and we need to check certain things, like for example, the sign of certain expressions numerically, so we get the numerical assistant proof for the spectral property. So now I'm slightly debating. So I'm doing okay with time. I can talk a little bit more about the theory, and I would like to show a couple of pictures. I think I can proceed with a little bit more of the theory, and then at the end I'll show you some of these snapshots. So the class B, what happens is that we take our solutions, okay, in HS, so the derivative, because remember we have 3 spatial derivatives, we'll put it in the S minus 3. Okay, so that we consider that they are defined in the classes, and then when we consider the equation, this is basically just the sum of 3 functions belonging to H minus 2, right? So this is not the, we don't have local positive in H1, so we just have, we use what we have. Okay, so now the weak convergence. So we select the time sequence and look at the weak convergence of our U along this time sequence in H1, and we define this element U tilde. So then we show that this U tilde is in the class B, and it's also orbitally stable. Then the trick part was understanding really the U tilde. And what we get is because we're so close to the soliton, and soliton has the exponential decay, we do have this exponential decay in space. So that's the beauty of I guess the KdV is a Zakharov-Kuznetsov equation. And then with the spatial decay, then we apply it in several places. So one of them is, this seems to be new, that when we look at the virial, it's basically just the virial. And well, we use it for the projection of the U tilde. So that works fine, no problem. And what we use it for when we get the boost in the regularity. So what does this mean is that, well, we take U tilde in H1, we take this weighted U tilde in L2 and Lx of 2, and this allows us to get our functions in H5 force. So we get 5 force regularity, although it's average in time, but if we apply the Rebovent estimates, then we can get L infinity regularity, and then if we keep bootstrapping, we'll update it for any S greater or equal to 1. So that's the regularity boost. So basically we get, to recap, U tilde, so remember that weak limit. It's a smooth exponentially decaying solution to the 3D, and we have now the very nice regularity for this. So the rigidity, or the Liouville type theorem, is that, okay, so if we have such solutions, okay, U tilde, then as you would expect from Liouville, U tilde turns out to be nothing else but a soliton, right? So it will be exactly Q with these parameters which are dilated like that. Okay, we prove it by contradiction. And the main part, I'll just say that's the linear Liouville theorem, where we introduce the linearized version. You can notice that there's a linearization happening here, and there will be other parameters associated to the linearization to the soliton, and that's where the orthogonality conditions will come into play. So you can see that this is the one which comes from the kernel, the gradient of Q, and that Q squared, that's the one which we use to show that if we have the uniformly in space-time spatial localized, so this is like a virial, then it turns out that we have nothing else but this W will have to be 0, which means that our original solution will be exactly just the soliton. I guess I'm going to skip this part, but let me look. So the approach which was introduced in Martel and Merle is to look at the adjoint problems. So instead of the W, take the linearized operator of the W and study the problem for the V. So if we recast it in the V, we get this, a certain equation, okay, where alpha is determined. So basically it gets upgraded to the equation something like this. And to determine the alpha, that's where we use the orthogonality conditions. So for example, one of the things which was done in the study of asymptotic stability in the 2D ZK and the way how Muniz and the company chose the orthogonality conditions, they had an equation which is like this, and this is also how it works in the KdV. You can you get only just this linearized equation without this funky term, okay? And of course, that's what creates the problem. So when we look at the virial, there is a bilinear form which shows up and which has 2 parts. And the first part, that looks quite nice, because if, like, for example, 1/2, we know that the spectrum will start from the 1/2. There's something like a Laplacian, although with different coefficients, but that's also not really a problem. Maybe there's a Q squared. That's also, there's a little bit more complication with this, but it's still not a big problem. But then we have a term which comes exactly from that extra term, which we just saw. It's the self-adjoint operator, and Q is not explicit. It's very hard to study this. So this is where we need to study it really to understand the spectrum and to show the coercitivity. So we want to show that this is the positive definite. Basically, we need to understand the spectrum and show what the eigenvalues are. And but that's possible to do. So we get this and we show how much we lose in each of the directions. And so the bottom line is that we can show that this will be positive definite, and it will finish the proof of the asymptotic stability. Okay. But before, so I finish now, I will show you, promised a couple of other 3D, sorry, no, I got, yeah, here, okay, so 3D plots to see how things happen. So the one which I want to start is over here. Here we are. Okay, I think we can see this. Okay, so now you have to pay attention because the pictures, it's not a movie, but the pictures will be changing. And for example, you can see how the radiation is starting to go, and it's extending. Okay, so this is computed together with Christian Klein and Nicola Stoilov, and what they're using is the periodic domain. So you can see that there's a little bit of things coming up from the very right front, right? So kind of radiation comes back because of the periodicity, and you can see it a little bit more. But the angle of the radiation, that's exactly the 60 degrees as confirmed. Now let me show you just a little bit more of how the radiation is forming over here. Okay, so, and the next stage is like this, and like that, and it goes like this. Okay, so that's the radiation coming up. Now, actually, just to really confirm that this is 3D, and so there's the isoplots for the X, Y, and Z. And so we take just the Gaussian data, and then it starts getting into this soliton. But to the left, if you pay attention, this is how the radiation is starting to come out. But if you start measuring that angle, it will be 68 degrees as well. So you can see that it keeps going and radiating. Okay, so again, so that's what we start, and then it the radiation spits out into the cone, which is the 60 degrees, and so on. Okay, the next I wanted to show, one of the interesting questions, which is this one. So this is not integrable equation, but even if there would be integrable equations, so the scattering theory does not so far let us understand the behavior solutions where you have a very slow decay. So like slow polynomial decay. So here we take a data which has polynomial decay, although maybe not very slow, but something like 1/x to the 10th. And we can see how the soliton progresses, except we see that it basically goes into the dispersion, so we don't see formation of the soliton. Of course, the radiation that comes from the right, but this is an interesting thing to investigate how the solutions will be decaying. This is the 3D regular Zakharov-Kuznetsov equation, and right, so we don't see the formation of this soliton for the polynomial decaying data. And I'll take one more minute to show maybe the interaction between two solitons in the 3D. So because we know, like, they have been worked where you see asymptotically, but what the interaction, how it goes. So let me just show you how things happen. So we have two solitons here. One is a little bit more concentrated, one is a little bit less. So they approach. So interaction happened. They start separating. Okay, there was, like on the previous one, there was a little bit of, you could see a little bit of radiation on the left going on, and they keep going their ways. Okay, so of course it's an interesting question to investigate the interaction, how and when, but I guess that's for the future. So I think this is, okay, let me come back. I think this is all that I wanted to say. And thank you so much for your attention and listening or even coming to this talk.